So I have equation 1. Maybe it's this one. And you manipulate the equation, right? Manipulation. And you sometimes forget to think about this is a different equation. And you get to manipulate, things change. If you multiply and add and subtract, numbers change and shapes change. That's a different equation. So you have to recognize first equation, the equation you end up at after the manipulation is different equation, not the same equation. All right? But isn't that kind of the same? So try to avoid that kind of vague expression in mathematics. 7 is different from 3, right? Anything different is different. It's different equation. But what we want from equation is a solution. That's what we want. If you look at equation, what you want is what is the solution of this equation, right? So by looking at this equation 1, you can think of, not the answer, you can kind of imagine there is probably answer to it in the back of the book, whatever. There's answer to it. And this one is a different equation, right? Correct? And then there's a different, you can imagine there are different sets of solutions assigned to that. And you believe these two things, solution 1 attached to equation 1, solution 2 attached to equation 2 is exactly the same. That's why you did the manipulation and put down the solution 2 as an answer for solution 1, right? Okay, so is these two things are really the same? Not always. This is the solution, is included. This is the kind of standard notation. Solution 1 show up in a solution 2. But maybe in the solution 2, you have unwanted numbers listed in there. Maybe solution 1 is really just 0 and 1. I hope you're familiar with the set notation. The solution to the equation 1 is 1, 0, and 1. And you go through the manipulation. You look at, if you solve this equation 2, you end up at 0 and 1 and 5. It's potentially get bigger. But many times, they are the same. So sometimes we don't think about that. Just whatever you get from solution 2 is my answer. But you will see some examples in this section that you have to rule out that 5. Only some of them is actually the solution to my equation. All right? The best way is that, okay, I have 3 things. I'm going to check if the 0 is a solution and 1 is a solution and 5 is a solution. Just plug that number back into the original equation and rule out which one works and which one doesn't work. Does that make sense? Yeah, that's one way. But often students ask, is there a better way than just plugging back in? It seems like it's tedious and sometimes you make mistake while you're doing that. So here's the final answer to the manipulation involves adding numbers both sides, subtracting numbers both sides, multiplying numbers both sides, dividing numbers both sides. Does that make sense? That's how you manipulate equation. Sometimes you square both sides, right? Yeah, this is a problem. When you square both sides, it got bigger. In here, usually you don't get things bigger. One more thing is that in the manipulation, if you involve multiplying non-constant, if you multiply 7 both sides, 7 is constant, right? So you know exactly what's happening. But sometimes you multiply both sides by x minus 5. Then x minus 5 is not constant, right? Then it can cause a problem. Those two things are the only spot that in this realm of course that can cause a problem. Potentially the solution set got fattened, enlarged. If you don't involve squaring, if you don't involve multiplying both sides by non-constant, you're safe. Whatever you get at the end is just simply the same solution as the original. This is a little theory I'd like to go over before we learn one method after another. Is this rough discussion make sense? So when you manipulate, watch out. Am I squaring? And it's going to cause a little bit of a problem. If you're cubing both sides, it's okay actually. It's even exponent is causing a problem. When we're actually looking at that example, we'll try to understand why that is causing a problem. All right, so here is example.